was dealing with the properties of fluids at rest. See, when of all the topics that we have considered, be it buoyant force, why in case of buoyant force, the upward vertical force was acting the weight? Because no other force was acting and the fluid wasn't moving. So upward forces could balance the downward forces because the fluid was at rest. So that's why everything we have considered under hydrostatics. Now our fluid will be in motion. Means we'll be considering properties like acceleration, velocity of the fluid, like these. So all these phenomena are considered under this branch of physics that is known as hydrodynamics. Means now the fluid is no more at rest, the fluid is in motion. So we'll be dealing with all the properties that we can encounter when the fluid is in motion. So the branch of physics which deals with the study of properties of fluids in motion is called hydrodynamics. Clear?
Yes.
See, the first concept that we get under this branch, hydrodynamics, is the concept of viscosity. See, whenever a solid surface moves over another solid surface, if two solid surfaces move on one another, then their relative motion is opposed by which force? If this is the direction of a frictional force, exactly. Their motion is opposed by force of friction between these surfaces. So this friction that you must have studied in your chapters like laws of motion, this friction is solid friction, right?
Yes.
See, the situation is similar in case of fluids. When we talk about fluids, the situation is similar. What happens is the liquid or the fluids layers, these are separated. So we see it as a whole, but there are various layers of the fluid. All right. So when a layer of fluid moves over another layer while moving, when the fluid is in motion, when one layer of the fluid moves over another layer, then their motion will also be opposed by some force. Yes or no? Similar to the situation that we have seen in case of the solid friction. So when a layer of fluid moves over another layer, their relative motion is opposed by the internal friction of the fluid itself, not the solid friction, the internal friction of the fluid. So this property of a fluid, this property of the fluid friction, you can say, that is known as what we call viscosity, the thickness, the opposition that one feels when the fluid is in motion. So viscosity is the property of a fluid moving fluid to oppose the relative motion between its layers is called the velocity of the fluid. So viscosity is that property of a fluid that indicates its internal friction. When you talk about internal fluid friction, that comes into action. So obviously, the greater the viscosity of a fluid, the greater is the force required to cause one layer of the fluid to slide past another layer. So if I say this is the direction of the movement of the fluid, which are indicated by these pink arrows, can you tell me what should be the direction of the viscous force acting?
Left side.
Left hand side, the opposite direction.
Yes.
Similar to the solid friction that we have seen. When the body is moving, suppose the body is moving in the right hand side, then the friction acts on the left hand side so as to oppose this motion. Similarly, in case of viscosity, the force that comes into action to oppose the relative motion between these layers, that force is known as viscous force. The force which exhibits this viscosity phenomena or the property of viscosity, that force that we get is known as viscous force. All right. Like you can take an example of honey and water. If you have honey and you have water, then when, let's take example of honey. If honey is moving, means the fluid is moving, then do we feel more opposition in case of honey or in case of water?
Honey.
Honey. Because the viscosity is more. And thereby the viscous force that we feel is more. Understood?
Yes.
So viscosity is the internal friction of a fluid which opposes the motion of one layer of fluid past another. And the forces of attraction between the molecules of moving fluid determine the viscosity of the fluid. So is this clear to you?
Yes, it's clear.
And there's this definition as well, which is in written, that viscous drag. Viscous drag is this only. This is known as this backward force that we face, that is known as the viscous drag. The viscous force, the other name for the viscous force is viscous drag. So backward dragging force is developed which opposes the motion of the liquid. That is, still we are talking about the viscous force only. So it acts tangentially on the layers. It acts tangentially on these layers, means in this direction, opposite to the direction. When a liquid or a fluid flows, a backward dragging force, this backward dragging force or viscous drag is developed between its layers that retards the motion of the liquid. Definitely, because it opposes the motion. So the viscous drag acts tangentially on the layers of liquid. So do one thing, note down the definitions.
Okay.
And if you have any doubts, you can ask me.
Done.
So is this topic clear? What is meant by viscosity and the viscous force?
Yes.
So let's see on what factors does this viscous force depend. So whenever you are asked to tell about the cause of viscosity, so remember the cause of viscosity is in the intermolecular forces between the layers. All right.
Okay.
See, I have just enlarged two layers of the liquid. Means if these are the layers 1, 2, then I've just enlarged them. There are various layers of the liquid, so that is what I've shown you. So if this is one layer of liquid, so let's say the area of this whole layer, this is what I'm tracing, this whole layer is A. And similarly, the area of another layer of the liquid will also be A. So these are the layers of liquid. Now see what happens. If I say this layer of liquid moves with velocity V, all right, this layer of liquid is moving with velocity V. So when it moves in this direction, there will be a relative separation between them.
Yes.
So let's say the position of these layers is changed by dx. The distance between these two layers is dx. So now see, if I say this was also moving with velocity v, then because of the change in position, will we get another velocity as well? Whenever there is a change in position, we get velocity.
Yes.
So see, if I say let's add dv, some small amount dv. So dv is the change in velocity when the position of the layers changes by dx. Is this clear?
Yes.
Okay, now you tell me what should be the direction of viscous force?
Opposite.
Opposite. So left or right?
Left.
Left hand side. So the viscous force will be acting on the left hand side because the two layers are moving on the right hand side.
Yes.
So A is the area of layers, and see these two layers are actually overlapping. Just just for your understanding, I have just separated them, and this distance is also
Okay.
not that much. Dx is a very small distance. So these are overlapping. And this dv, I'll write about this dv as well so that you don't forget. dv is the change in velocity. Why? Because of the change in position.
Okay. So the upper layer will be faster.
Yes, upper layer, you can see this dv, this change is very small. And see, this layer will also be experiencing some dv because of the layer which is below it.
Yes.
So that's why the whole liquid will flow together.
Okay.
Position by dx. So these are the conditions. Now see one thing. Whenever we say rate of change, we divide the quantity by time. For example, if you have velocity, how do we write velocity? Rate of change of distance or
Yes.
displacement, exactly like this. So this
Yes.
rate of change, what does that mean? It means displacement divided by time. Similarly, when we write acceleration, we write velocity divided by time. So velocity divided by time, it means rate of change of velocity. Yes?
Yes.
Now see, whenever any quantity is divided by time, we simply write it as rate. But if the quantity is divided by distance instead of time, then we call it as gradient. So if I say dv means this change in velocity, and the relative separation between the layers means divided by dx. Can you tell me what should be the name of dv by dx?
Time.
What?
It will give us time.
No, it won't be time. From this formula, even if you're saying that v by x is 1 by t, not time. This see, when any quantity like displacement was divided by time, we called it rate. Had any quantity been divided by distance, or whenever any quantity changes with respect to position, then we say gradient. So if velocity is divided by distance, we see it as velocity gradient.
Okay.
Like in 12th standard, you will get potential. And when this potential will get divided by distance, then we call this whole term as potential gradient. So gradient is when any quantity is divided by distance. It means when the quantity changes with respect to position. The way we say distance is changed with respect to time, then that is known as rate. Similarly, if any quantity is changed by distance, then we call it as gradient. So similarly, dv by dx, that will be known as velocity gradient. Understood? Gradient and rate, difference between
Yes.
gradient and rate. Now see, on what factors does the viscous force depend on? See, viscous force firstly depends on the area. What area? Area of the layers of the liquid that we have seen. This area. Okay, so first factor is the area. Then we have just discussed what is meant by gradient. So this viscous force also depends on the velocity gradient, means dv divided by dx. So viscosity first, viscous force first depends on the area. Secondly, it directly depends on the velocity and inversely proportional to distance, means directly depends on the velocity gradient, right?
Yes.
So if I write these factors together, if I write these two, combining these two factors, I'll get my viscous force is proportional to area as well as directly proportional to the velocity gradient. Now, if you remember, can you tell me how do we remove the sign of proportionality?
By adding constant.
By adding constant, yes, and with an equal to sign. That's how we convert the proportionality into an equation.
Yes.
Fv will be equal to a constant that is represented again by this symbol eta. We have already discussed about this symbol in shear modulus, if you remember, modulus of rigidity.
Yes.
Remember?
Yes.
So over here, it denotes something else, it represents something else. So eta is the constant that is used. Now the rest of the terms. A dv over dx. So this is the formula of viscous force, where C, eta is basically coefficient of viscosity. So this coefficient of viscosity depends on two things. Firstly, this coefficient of viscosity depends on the nature of material. Depends on nature of material. Means viscous force is itself a material dependent property. That's how we got the example of honey and water. Honey is a different
Okay.
material, water is a different material. So it
Yes.
depends on nature of material. Secondly, the coefficient of viscosity also depends on temperature. So these are the two factors on which the coefficient of viscosity depend on. And this is the formula for the viscous force. Clear?
Yes.
All right. And see how it depends on temperature is that the coefficient of viscosity of a liquid decreases with increase in temperature. So it means you can say inversely proportional to temperature.
Okay.
All right. So just
Yes.
note the factors and these points for the coefficient of viscosity. And wherever you get stuck in between writing, just ask me.
Done. Done.
Okay, just try a very easy question based on this.
Okay.
And note this point also. First note this point and then write down this question and try. See, SI unit of the coefficient of viscosity is decapoise. So unit will discuss it,
Okay.
but for the time for solving this question, I'm telling you the SI unit is decapoise. So don't convert it into anything.
Okay. The answer is 40.
How much is your coming? The viscous force. How much is coming?
Yes, 40.
Only 40.
Yes.
Did you convert this millimeter into meters?
Oh, no, I didn't.
Just check up your mistake once.
Okay. $40,000.
Yes, now it's correct. 40,000. I think because of 10 to the power minus 3,
Yes.
that was
And the unit is newtons.
Newton. Yes, yes, because it's a force. So
Yes.
SI unit will be Newton. Whether it's any kind of force, the SI unit for the force remains Newton.
Okay.
Okay, do one more question. I'm writing it over here. So you note it down as I.
Okay. Can you help with this one?
Yes, you're saying something?
Yes, can you help with this question?
Okay. See, we have to calculate the horizontal force required to move a plate of area this much, of moving with velocity this much, when it rests on a layer of oil. See, when we have any surface, let's say this is oil placed on this surface. So this oil is actually acting like a thin film.
Yes.
So whenever any object has been kept on it, this layer of fluid will be exerting viscous force on it. So that's what the question is asking us. This force, horizontal force, that is the viscous force only required to move a plate. So the formula for viscous force is eta A dV divided by dx. This is the formula. Now see, let us see what all terms we have. Eta, coefficient of viscosity. It's 2 Newton second per meter square given.
Yes.
All right. See, area is also given to you, 2 into 10 to the power minus 2 meters square. Velocity is given to you, 4.5 into 10 to the power minus 2. And the thickness of the layer is given to you as 1.5 into 10 to the power minus 3. So when calculating FV, you just have to put all the values. Coefficient of viscosity is 2 multiplied by area. Area is 2 into 10 to the power minus 2. This much. Then velocity. Velocity is 4.5 into 10 to the power minus 2. And then we have the thickness of the layer of the fluid, that is divided by 1.5 into 10 to the power minus 3 that we have. Now see, if you just leave this apart, you will be getting 3. 15 multiplied by 45 is 3. So 1.5 multiplied by 3, you will be getting 4.5. So now see, 2 multiplied by 2 is 4. 4 multiplied by 3 is 12. So 12 you have. 10 to the power minus 2 multiplied by 10 to the power minus 2. This will give you 10 to the power minus 4. Yes?
Yes.
Divided by 10 to the power minus 3. When this 10 to the power minus 3 will go on the numerator, it will be 10 to the power positive 3. So
Yes.
10 to the power 3 multiplied by 10 to the power minus 4. It will give you 10 to the power
Minus 1.
minus 1. So it's 12 into 10 to the power minus 1, which is simply 1.2 Newton. Clear?
Yes.
Okay, so just note down the solution.
Done.
Okay. Now see, regarding this constant eta, we have just discussed it briefly above. Now let us discuss it in detail. Coefficient of viscosity, that is eta. Now see, definition of eta is coefficient of viscosity is defined as tangential force required to maintain a unit velocity gradient between two parallel layers of each unit area. This means that Fv is equal to eta A dV over dx. If I say dV over dx is 1 and area is 1 and this whole term is 1, will eta be equal to viscous force?
Yes.
Yes. So that's how we define quantities in physics. If the velocity gradient is 1 and your area of the layers is 1, then your coefficient of viscosity will be equal to viscous force. So the definition of eta is, it is the force required to maintain unit gradient velocity per unit area for each unit area. Yes or no?
Yes.
Right? And see, these are the
Yes.
2 points that we have discussed previously only. That viscosity of ideal gas is 0 and viscosity is inversely proportional to temperature. So this is mainly for liquid. If the case is for gases, then it is directly proportional to temperature. Now, see, if we see the unit of coefficient of viscosity, so the formula is this eta A dV over dx. If I wish to find out the unit of this term, then I have to transport all the terms on the left hand side. So eta would be F dx divided by area into velocity. Now you tell me, what is the SI unit of this term? Force.
Newton.
Newton. This term.
Meter.
Meter. Area.
Meter square.
Meter square. Velocity.
Meter per second.
Meter per second. So this would be meter. Seconds would go up. So that's how I have written previously also the question that we did here. Newton
Yes.
second per meter. That's how the unit came. So the SI unit of it will be, eta will be Newton seconds per meter square. So see, if I write regarding the SI unit of eta, means the coefficient of viscosity, it would be Newton meter square inverse per seconds. See, this quantity that we are getting, Newton seconds per meter square, this, we can write decapoise instead of it. So that's why in the first question we have seen decapoise, and in the second question we have seen Newton seconds per meter square, because both the quantities are same. Remember, we used to write Newton per meter square as
Stress.
no, that
Pressure.
was the formula for pressure as well as stress. You're right, but Newton per meter square. One more thing, how we used to write the SI unit of stress and pressure. Remember? Pascals. Pascals.
Yes.
So the way Pascals and Newton per meter were similar. Similarly, we have this and this similar.
Okay.
Now see, if I write the CGS unit of coefficient of viscosity. So Newton's CGS unit. What is Newton's CGS unit?
Dyne.
Dyne. Yes, right. It's dyne. And for meter we have centimeters square. And seconds would remain the same. Time is same. Now see, this quantity that we are getting, dyne per centimeter square seconds, this is known as poise. So if you are asked to tell about the SI unit of coefficient of viscosity, you can write it as this or decapoise, and the CGS unit then becomes poise. Clear?
Okay. Yes.
Now see, effect of temperature on viscosity, that I have already written above. if you have to write about the temperature, you have to mention it separately for the vapor state as well as for the liquid. So this is directly, this is inversely proportional to temperature, and in this case, this is directly proportional to temperature. So this I have written earlier also
Yes.
over here. All right, so note all these points.
Done.